Hello, everyone. My name is Teona Velkoskam, and today we're going to do presentation about Spike Intelligent Scheduling of Hubble Space Telescope observations. And we are team 16. Okay, let's see the overview. So from the overview, we can see that first I'm gonna give some introduction about the topic, then I'm gonna talk about HST scheduling, then feasibility constraints, preference constraints, consistency methods, and in the end, I will talk about computational aspects. After I'm done talking, Sai will continue with his part. So let's see the introduction first. Spike system is defined as a general framework for scheduling. Spike system has been developed by Space Telescope Science Institute. Spike system was designed for generality and flexibility, and it also has been adapted for several other astronomical scheduling problems, as well as to problems unrelated to astronomy. Okay, we can go on the next slide. Let's see the HST. So the HST stands for Hubble Space Telescope. The HST has provided important new capabilities for astronomical research due to its unsurprised combination of wavelength coverage and angular resolution. The HST was launched in April 1990. HST is currently engaged in a full research program that has been produced many exciting results. The HST scheduling problem is one of the largest and the most complex scheduling problems that facing the counting basis. So we have approximately from 10,000 to 3,000 observations that are scheduled per year, and each one of those is subject to many operational and scientific constraints. Okay. Let's see the, okay, we're just going to continue the HST scheduling. The amount of observation time available is the primary resource constraint for the HST scheduling, but there are some other resources. Some other resources are the amount of data which can be processed by communications and ground systems, onboard tape recorder storage, onboard command computer storage. The HST operates largely in a pre-planned mode, but it can also be disruption. It can also have disruption to the schedule that occur for a variety of reasons. Okay, the disruptions we have the most known and rare disruptions are targets of opportunity, but there are other schedule disruptions, and they result from spacecraft anomalies, loss of communication contacts, and changes in observing programs. Okay. This is just showing the range of timescales for HST scheduling constraints that are covering more than 6 orders of magnitude. Okay, let's go to the next one. Okay, now let's see the feasibility constraints. So feasibility constraints state conditions or times when activities may or may not be scheduled. For this type of constraints, the scientists use the term strict and hard or hard constraint. If we ignore the feasibility constraints, it can possibly lead to unimplementable schedules. Some examples here are provide a minimum of 2 months between an observation and repeat observation on the same target. don't ever schedule an observation when the sun is within 50 degrees of a target, and never roll the spacecraft more than 30 degrees from its nominal orientation. Okay, let's see now the performance constraints. The performance constraints state quality judgments on scheduling constraints, which are preferred but not required. These are usually based on objective or subjective factors. If we ignore the performance constraints, it can possibly lead to unacceptable suboptimal schedules. Some examples here are minimize scattered light from the bright limb of the Earth, maximize the chance of successfully acquiring guide stars, and place an observation as close as a nominal roll as possible. Okay, let's see now the consistency methods. The node consistency points to removal from consideration of domain values, which cannot be part of any solution. Here, the determination is made based on unary constraints. Arc consistency. Arc consistency points to removing values from the domains of variables to satisfy binary constraints. And the path consistency points to the inference of additional or binary constraints based on those explicitly stated. Okay, now let's continue. Yes, to the next one, computational aspects. It's required for the implementation of suitability function on digital hardware to be discretized, either in time, value, or both. In Spike, any fundamental discretization in time has been avoided for two very important reasons. First one is it introduces an artificial time granularity into the problem, and many important constraints yield suitability function which have long intervals of constraint values, and because of that it would become inefficiently represented by many of identical values or for many discrete time points. To improve in this field, the scientists adopted the discretization of suitability function values, which allows for the suitability function to be represented as piecewise constant functions, or PCFs. Other advantages of PCFs are they are close under all the common operations required for multiplication of suitability function, such as multiplication or maximum. And the second one is the cost of storing and combining PCFs is proportional to the number of intervals with discrete value to the, and not to the size of the scheduling intervals. Okay, so Sai will take on from the presentation.
Yeah, thanks Tiana for doing your part. And so from now I'm going to explain about these 5 topics: the constraint satisfaction problem, the Spike CSP toolkit, the time sampling, scheduling sets in Spike, and key steps followed in Spike. So if we see the constraint satisfaction problem, we can go to next slide. Yeah, if we see the constraint satisfaction problem, so constraint satisfaction is the process of finding a solution using a set of constraints. So those set of constraints are basically used to enforce some conditions on the variables which are available, and these conditions must satisfy while solving any problem. So this CSP denotes a set of variables and constraints with variables denoting the preferences and values associated with them. And Spike CSP toolkit, for any type of CSP that is implemented, the two above classes must be adjusted. If we see in the, as an example, if we see in the figure, like for solving any kind of puzzle, so there should be some constraints. So we have to follow those constraints to solve the puzzle. Let's say the constraint satisfaction problem is made up of multiple variables, as we discussed, and by overcoming the constraint violations we will assign a consistent collection of values to all these variables. So we need a plan to issue utilizing a constraint satisfaction problem for each variable, so that we can schedule an activity to solve the problem, and we can further segment the schedules into interval for each schedule, so that it will help us to calculate the variables which we are defining in our problem. And it can be employed in a variety of sectors, variety of applications, like tackling like solving these puzzles, or in some kind of investigation stuff. So yeah, we can go to next slide to talk more about the Spike CSP toolkit. So yeah, as my teammate has already explained, that it is developed by Spike Space Telescope Science Institute, and it is the Spike CSP toolkit is basically a scheduling software in support, and it is in support of the Hubble Space Telescope, and it is mainly used for planning and scheduling. So this is mainly implemented as a collection of object classes and methods, and some of the few abstract classes used in this Spike CSP toolkit are inconsistent assignments, locked and ignored variables, removable and restoration of domain values, constraint weights, constraint caching, assignment history and snapshots, so and capacity constraints. So to talk a little bit about these abstract classes, inconsistent assignment are the problems where there are no solutions to these CSP problems. So there is only a key factor involved in it, and at every stage these are allowed to include assign values that are stated inconsistent with other assigned values. So because of these significant reasons, we utilize the information related to these constraints and assign them to do the tasks during the scheduling search. And the second one, locked and ignored variables. So in this, the variable must have a specific value assigned to it, and that can be considered or ignored later if it doesn't have any value. And dividing the schedule into different activities into two different kinds, like active ones and inactive ones, so that some of them can be overlooked until certain conditions are met. And the constraint weights is basically basically we will define a desired set of weight to the constraint, and this quantity of conflict count can be increased in each violation. So these will so this weight will become more important while we have any conflicts in these constraints. And constraint caching gives us the influence of assigning values to a current collection, and there are significant benefits of this, like it allows us to easily retract any system that has any current assigned values, and it also helps us in explaining the constant domain assignment. And the other one, assignment history and snapshots, so it has the history system that saves the current set of assigned values, so that it will make sure of the previous states that we have worked on to enhance the runtime performance of the toolkit. And the other one, capacity constraints. So this toolkit basically implements the resource capacity constraints as universal class, so that we can map it from one to many class or many to one relationships that we can use in our toolkit. So we can see the time sampling in the next slide. So time sampling is nothing but the scheduling interval for an activity that is distributed as part of CSP variable domain translation. So as part of translation into CSP network, in every activity, scheduling is sequence of process. As a result of how we express intervals is really crucial, so that these set of intervals, these sampling periods should be shorter than the scheduling constraints real duration. So it is necessary to address how to divide this representation of time when we compare it with the natural time discretization. So if the condition meets, then we will choose the optimal sampling strategy to treat or prevent the stringent limits for each particular activity, so that it won't affect the other activity that is going to take place after this. So this choice mainly depends upon entire interval, without excluding it or not. So in the next slide, we are going to see about scheduling sets in Spike. So as we can see, Spike mainly addresses the schedule construction as a restricted optimization issue, and it employs multi-start stochastic repair, a heuristic repair-based scheduling sets that we use. So the key steps involved in this technique are trial assignment, repair, deconflict, optimization, and oversubscription. So trial assignment is nothing but it is the first step and we mostly what we do is we just have to guess the activities based on the heuristic search and assign it to them. And in repair, we will eliminate the constraints, and we will use heuristic repair strategies until there are no conflicts to eliminate the violations in the constraints. And deconflict, in order to create a realistic timetable, we will remove any of the constraints that are present by running different trials and testing different probable estimates, as well as making them more heuristic, so that we can use this technique to utilize the Spike tool in most viable option. And there are primarily two other aspects to consider in it, like optimization and oversubscription. So in optimization, both the trial assignment and repair heuristic functions pay close attention to the most suitable functions, resulting in a schedule that is to be optimized. And in oversubscription, all the activities are pre-planned, so that there is no way to avoid oversubscription. So as a result, this stage entails a high level of relevance that is to be resolved. So the key steps involved in Spike can be shown in the next slide. Yeah, so the key steps are trial assignment heuristics, repair heuristic. So trial assignment heuristics are nothing but the trials that are to be done on different combination of variables in order to identify the most powerful combinations. And the repair heuristics, these repair heuristics use conflict count of information, that is number of constraint violations on the scheduled activities. So to use it to, we will use it to the full potential. And in deconflict, so in order to remove these conflict activities, the oversubscribed schedule, we use deconflict. And schedule quality measures, it includes number of observations observing the time and degree of performance. And the fifth factor, rescheduling. So this is basically used to reschedule the task that we are doing. So in Spike, it can be scheduled in variety of methods. I mean, the scheduling can be done in a variety of methods, including task locking and conflict cause analysis. So a group task or task can be grouped together in one particular scheduling location, or it can be done in multiple locations too. So one opportunity at a time scheduling can be targeted, and many spikes support rescheduling in the user interface that the user is working on. So from now on, my friend Dinesh is going to take over to present his part.
Thank you, team. I'll take it on from here. My name is Dinesh Anavoina, and we are from Team 16. I will talk about Spike and Hubble Space Telescope science scheduling, which includes personal preparation, transformation, long-term scheduling, short-term scheduling, and implementation of Spike technique. So it starts with the planning and pre-scheduling of Spike technique, which includes some of the proposals from remote proposal submission system and proposal entry processor, convert to SPSS format, and long range scheduling, short range scheduling, and finally some POCC detailed command schedules for HST. When it comes to proposal preparation, an astronomer who wishes to use the Hubble Space Telescope must submit an observing proposal that details the observations to be performed. This proposal serves as the main source of information for the planning and scheduling process. Observation proposals are handled through the remote process submission system, which is RPSS, and the proposal entry processor, which is PEP, which includes electronic submission by astronomers. When it comes to long-term scheduling, a two-tiered approach to scheduling was used since the Hubble Space Telescope scheduling challenge spans such as a wide range of timescales and tens of thousands of activities. A long-term plan is one that lasts around a year and assigns responsibilities to certain weeks or portions of weeks. Week-long portions are derived from long-term plan for short-term scheduling. The Spike system is used for long-term planning. And short-term scheduling operates on a weekly basis, building a calendar from the long-term plans list of SUs. Once the activity sequence has been determined, the high-level spacecraft commands are linked to calendar activities. This is the main point of using this short-term scheduling. When it comes to implementation, as a result of the method, which we call as a Spike, Science Mission Specification, SMS, in this section, we'll look at some of the implementation issues of Spike, which is a real-world application of artificial intelligence technology. Spike was created on Texas Instruments Explorer LSIP computers in early 1997. The Spike graphical user interface was written fully in Command LSP and used the flavor object system, while the remainder of the system was developed entirely in Common Lisp. At the time of the HST launch, STSCL had a complement of 8 mini explorers and explorers for Spike operation, development, and testing. Operational experience. The Spike technology was used for the first time in Cycle O to help with HST scheduling. The timetable for SV observations was set by NASA. The STSCLs, the commands, used Spike to check the timing of GTO observations and schedule them during weeks. When time was available, planners used Spike in an interactive way to schedule these ideas. In Cycle O, they presented individual proposals on timeline displays and identified the best dates for observations. Several atomic scheduling technologies were occasionally used when making manual commitments. Scheduling for early Cycle 1 proposals was also extremely participative, while little reliance on high-level automated schedulers. Application of Spike to other astronomical scheduling problems. Spike has been modified to address a variety of astronomical scheduling problems. 2 of them have taken off or about to take off, while the others are still in prototype or planning stages. Adapting Spike for various situations was deliberately pursued during its development. Each instance provided feedback on the method, which led to improvements from one iteration to the next. Spike's adjustments for these conditions demonstrate the flexibility of Spike scheduling. Spike was designed in such a way that new tasks and constraints can be defined without challenging the overall architecture as previously indicated. Overall, the Spike scheduling system, which is linked to a massive intricate ground infrastructure, has been supporting NASA's Hubble Space Telescope since its launch. Suitability functions which are used in Spike allow for an efficient description of many factors that influence real-world scheduling decisions. A resilient multi-state stochastic repair approach is used to produce schedules. Spike's versatility has been demonstrated by including long and short-term schedulings at various levels of abstraction in the same constraint representation and search framework, as well as adapting it for a range of other spacecraft missions and ground-based observations. That concludes our presentation. That concludes the technique Spike that we used in astronomical instruments. Thank you so much, everyone. Have a good day.